Good afternoon, everyone. Thanks for coming back from dinner earlier. I'm Charlie Su. I'm CTO and Senior Vice President of AndeStar Technology. Today, I'm going to talk about domain-specific acceleration by AndeStar V5 processor, which is an extension to RISC-V. So I'm going to give a little bit overview of AndeStar because some people probably don't know about us, and give an update of our latest processor. And I'm going to spend most of the time talk about AndeStar custom extension for DSA. So AndeStar is a 13-year-old CPU IP company. We've been doing this CPU for that long. And most of our customer products are in the consumer domain, so this is typical of those. And also some of our customer products most of them are kind of in the close to a consumer on the edge part, but some of them do go to the data center. And we are founding member of the foundation, the RISC-V Foundation, and we are a major open source contributor. As you can see, GCC, LVM, and Linux. And we also actively involved in the standard RISC-V standard extension. We are the chair of a P extension, PAC DSP CMD task group, and we are the co-chair of fast interrupt task group. In our task group, we are kind of actively involved in looking at and give some suggestion. Extendability in RISC-V is the best thing which enables the domain-specific acceleration. Acceleration is the key, but because the 80-20 rules is always applied, that means 80% of time spent on 20% of the code or logic, but for the rest of the logic, the power and area probably matter. And for the code, the rest of the code, its size matter in some application, and so is the performance, if you can take those law into consideration. So baseline processor are important too. So in this, we have this V5 architecture built on top of the RISC-V standard. We're adding so-called baseline extension, which will be basically generated, handled by our compiler and tool. And we also provide AndeStar custom extension framework for custom to extend instruction to accelerate their application. AndeStar has a 25 series processor, which announced in the past several months. And it's the smallest usable configuration for this N25 and X25, which is a 5-stage pipeline, single issue core, just local memory or TCM, no cache, no BTB, and running at 1 gigahertz. It can be just as small as 37K gate. That's for 32 bits, and for 65 bits, only 56K gate. And if you consider adding more features like caches, 32K, and full size of branch prediction, and double precision floating point, and MMU, and plus SMO. So we have different core, N core and NF core, and also A core. And it can reach from 1.2 to 1.4 gigahertz. This is the worst case condition. And we also had leading CoMark and DMIPS at this level of core, which is, again, 5-stage single issue and this kind of size. So today we're going to announce our new core, a very compact one called 22 series. It's based on our V5 ISA or V5E ISA, which is 16 register. Instructions are exactly the same. 2-stage pipeline with HB Lite members, and a lot of rich extension. It can have local memory, instruction and data, also instruction caches. That's very useful for the flash-based application, or you have memory sharing in the big processor. Multiply option, branch prediction, and up to 16 entry PMP, and UMO is optional. And we also, in addition to the members, we also have private peripheral port, fast I/O port to speed up the I/O control access. And wait for interrupt, wait for event, and power break, our unique digital way of doing frequency scaling. And vector and preemptive prick. So this very full reach of feature. And advanced option, like we're going to talk about ACE, and we are going to add in the DSP extension and floating point. And 28 HPC Plus can reach over 750 megahertz. And the smallest configuration is about 15K gate. And per megahertz performance is also very impressive. Almost 1.6 dBs per megahertz, no inline, that's ground rule, and almost 1.7 comma per megahertz. So that's kind of our offering for baseline. We definitely continue to develop more baseline, but today's main topic is to talk about ACE. So what is ACE all about? I mean, how do we deliver the ACE power to the customer? So first we deliver so-called baseline extension component from our RTL simulator and also all the toolchain, compiler, assembler, debugger, IDE. So if you don't extend it, this is what our customer will get today. And how do you extend it? You're writing C code, you're writing Verilog code, and you're setting some attribute. So we're going to have some example very soon. So with that, you can define scalar instruction, vector instruction can put on the background. You can have wide open access so that you can have more data to process. And go to our powerful tool, compiler, which name is kind of just made it up. So we are compiler and custom is the pilot. With that tool, we're going to generate the new instruction, the additional component needed because the new instruction defined, including extended RTL, extended simulator, and all the extended component for tools. And together with the baseline component we deliver to customer, that's unique processor custom have on their desktop. You don't need to go to our website and so on to do it to get the result. And also, we provide automatic cross-checking environment because we ask customers to define instructions semantic based on C and also audio design based on Verilog. So we can automatically put together the cross-checking environment for customer. So Mat32 will take 2 integer number and 16-bit portion matching up, multiply, and add into the first operand. So this is taking the first operand is input and output accumulator, ACC, and from GPR, and the 2 input also from GPR. And so that's all you need to write. So defining instruction, defining operand, and writing the CSIM is purely C code to define instruction semantic. With this, you can get everything I talked about in the previous page, except RTL. So how do you do the RTL? So you put the instruction semantic between AC begin and AC end. So in this case, it's very simple. You're using a Verilog way to extract the bits, do multiplication, and add it up. And also, the tool environment compiler will automatically generate the intrinsic function based on the instruction, so that your application just need to using the intrinsic function to do development. You never need to know what the instruction the mnemonic is, but it does exist. Okay, so now when you're doing this kind of the Mat32 instruction is kind of boring. You want to do a bunch of them, so let's vectorizing it. So we call, and when you do the 16-bit by 16-bit multiplication and add it up to 32-bit, it may overflow. So a serious user maybe would using the 64-bit accumulator. So it make it Mat64. So this is what you do. Yeah, so the purple part is what is different from the previous page. So you make the instruction vector by saying VEC, and instead of the GPR ACC, now we define a data type called rich ACC, which is 64-bit. Because we assume this is RV32 processor. And since you want to do a vector, so your data for what our definition now is from memory. So we call XY memory. Here you see the RAM definition for XM. Width is 32, and the address range is 12 bits, means 4K of 32 bits. The interface, you can ignore that. That's default for SRAM for now. And for vector instruction, you also need to provide a count, so how many times you want to do it. And so loop type, this is a fixed iteration based on count. We can also define something like while loop, so based on a condition. And stride by default is based on the element size. So XY, X-man and Y-man. So based on that, you stride the one for every iteration. So we have latency, and latency overhead is something specified for one time for per vector instruction. So this is all you need to do. The instruction semantic inside CSIM and AC begin and AC end is precisely the same as the scalar version. Okay. So with this, you have vector instruction doing a lot of 16-bit by 16 multiplication, accumulated to 64 bits, so you don't lose precision. Now, this instruction would take some time depending on the count. So it would block the main pipeline execution. So maybe you want to put it into the background. So we could call vectorization, meaning putting that into background. Okay. So all you need to do is change the instruction INSN to BG_INSN, put that into background. Then this instruction will execute in the background. So that's everything that you need to do, basically different from the foreground version. But we do have some option for you to control the parallelism, because you may want to limit some conditions so that you can use less resources and so on. And synchronization instruction is automatically generated so that you can check to say each background instruction is it finished or not, or even better, you have a bunch of background instruction is executed, and then you have one global instruction to check whether all of them are finished. So this would be automatically generated by the tool. Now next is with ring buffer, because when you're doing this kind of inner product-like operation, oftentimes your data will come in from memory, and you have limited the buffer to keep all the data. So how do you make that? So the previous vector condition is that you have fixed stride, continue move forward. But you may, if you ring buffer type, how do you do that? So for that we define it. Let's say you have 4 ring buffer would be active most of the time, and in your XMEM, then you define a 4 element address register and point to different ring buffer, so you can use that directly without reloading the address register. And so definition is very similar. So you define a range XADDR, and 4 number is 4. That means 4 the register element, and width is 12 bits because you need to address the XMEM, which is 12-bit address. And so what do you do differently? So the purple part is what is different from the previous page. So previous one, we're using your input specified as SM and YM for XY memory. But here you specify a specific address register associated with that memory access. So for XM, you have XADDR and with update mode, and YMEM with YADDR, and also with this update mode. And how do you update that in the C code? So basically, we define additional symbol based on the operand name. So for data operand, the second operand name data, then you have something like data_ADDR. That's for the current address, and so with that you can do any calculation for how you want to generate the next address. In this case, you increment it and you wrap it around on the this is the 512. Not 512. It's 128 element entry that you wrap it around. So 128 entry ring buffer, and then you assign to the next address. So that's all you need to do. And same thing for what do you do for data, and also similarly for the coefficient, the COEF. I didn't put the variable code here, but very similar. So we define the name for you to give you the current address, and user has the chance to kind of update it with the equation that they want, and assign to the new address a variable that we define with this convention. Okay. So with this instruction means that you do the math 32. So in this case, I didn't make it 64, but that doesn't really matter. So you do the math 32, and with the input from the 2 different ring buffer, and access that and do a computation. At the same time, you increment the ring buffer pointer accordingly. So we used to have a customer want to do everything on the general purpose register, so you can count how many rewrite port you need. So if it in this case, just I/O, you need 1 read, 1 write, and for the ring buffer address, also 1 read, 1 write. So you have 3 read, 3 write port. So it's kind of quite expensive. And they want 2 sets of this. So if you're able to define a special register for this purpose, that complete upload, I mean, move the pressure of a register port from the general purpose register to dedicated port. So sometimes when you write instruction, you have some different instruction, have some similar logic that you want to share, so that because they are not going to use at the same time, and they consume some area. So for example, in this case, you have a 16 by 16 multiplier, and you have instruction called math32 and msub32. So you can, using AC, share that pragma, and using the instant name to specify whether that instant is the same instant. If it is the same instant name, that means the same hardware. And the different instant name is different hardware. So you can see that math32 and msub32 can share that multiplier. So you can make this way depending on how complicated your module is. And actually, this example I showed it before in the workshop, but this is kind of want to put it as a complete package. So this is an example that gives you very wide input paths and it can to give the computation capability to the user. So because a lot of machine learning computation involved on matrix multiplication, so this is one example of doing 64 of 8-bit data and do the inner product of 2 vectors. So you can assume one of the input comes from the register because less change, and the other operand keep changing as you go through the inner loop. So you can define one is on the register, 512 bits, the other one from memory, 512 bits. And once you define the data type, you put that into the operand. So C and V are 2 512 bits data type. Then in the variable part, you just extract it like before and do the multiplication and add it up and to the inner product, IP, which is the output. And C code is similarly, you can do that. And we include the multi-precision library so that now the common operator knows this is 512 bits and can do that operate directly. And also, if latency is specified as a constant, our tool are going to automatically generate multi-cycle control. So in this case, the variable part would be a basic text 3 cycle, and the end of 3 cycle, the generated logic going to sample the output and then write it to the result. In this case, it's GPR. So this 64 addition is not going to take 1 cycle. So for 3 cycles, it happened to match our 25 series code pipeline well. So if you 2-stage and other different, then you can adjust the latency differently to see whether it matches your requirement. And intrinsic function will generate it automatically as well. And so the example are kind of simple for the presentation purpose. So if you have complicated logic there, for example, you can put while always loop there, everything except the module end, module begin and module end, because module begin is covered by the operand list. So when you have complicated stuff, you may want to debug it and so on. So tool will automatically generate the waveform control file, so you can go there to see what's wrong with the signal. If you running the cross-checking, in our environment, run the cross-checking and detect some mismatch. So in conclusion, the benefit is, so with this tool, we allow users to focus on the instruction semantics, not CPU pipeline. You don't see the CPU pipeline at all. We hide it under our high-level interfaces. And all the housekeeping tasks are offloaded to the tool, including OP code selection, OP code optimization. We'll find the best place to put into a code. And instruction decoding logic, Verilog and C, and operand mapping, operand access, update, no matter it's a register, general purpose register, custom-defined register, or custom-defined memory, and dependent checking with the previous instruction and the next instruction. It's all done. So with this, adding instruction, defining an instruction, like very similar to the ASIC design. You define the semantics based on the operand interfaces. And we also provide comprehensive support, so powerful instruction semantics, including a vector. I can put a long latency instruction to background. Instruction can have wide operand, so you can do a lot of computation there. That's kind of one of basically restriction of the standard CPU instruction. And we also automate generate verification environment development tool in all RTL code, except the semantic itself, which need to be developed by user. And software invokes the instruction by using interesting function, so not assembly code. So with this, we think Copilot really unlocks RISC-V potential for the domain-specific architecture or domain-specific acceleration. So with that, thanks for your attention.